Hello. Yeah, just one administrative announcement. There will be a photo session for this week, just before lunch. So at the end of these two talks, so please be there just before lunch at the end of the second talk from now. So now I'm giving to Benjamin to chair the session.
Thank you. So yeah, so first talk will be by Jitendra Kethepalli, who will talk about, from Cergy, who will talk about ballistic macroscopic fluctuation theory, ALA mapping to point particles. The accent on the A doesn't matter too much.
I'll change it. Thank you, Ben. Thank you, organizers, for organizing this such a wonderful conference and giving the opportunity to talk here. I'll talk about ballistic macroscopic fluctuation theory for integrable system, but by mapping it to point particles. What I mean will get clear as we go along. This work is basically two different works in collaboration with Andrew, Somo, Tridib, and Jacopo. So let's start. To understand non-equilibrium properties, it's a very fundamental thing. And hydrodynamics basically has the answer to average density profiles. But what about fluctuations? To understand fluctuation, we need a fluctuating theory. For diffusive system, this has been done by macroscopic fluctuation theory, but what about for ballistic system? The idea is there is a new framework called BMFT, Ballistic Macroscopic Fluctuation Theory, which addresses this. So what are these two different theories? In macroscopic fluctuation theory, basically you can express the current in terms of slow modes and fast modes. And these fast modes are coming because, I mean, fast mode is basically a noise kind of term. It's basically whatever is moving very fast. As a result, your current has a noisy correction. In the BMFT, there is no such term, or even if it's there, it's extremely small. So this will have a deterministic evolution. There is a stochastic evolution, not stochastic, but a noisy evolution happening in the macroscopic fluctuation theory. One example is symmetric exclusion, simple symmetric exclusion process for MFT, and BMFT maybe it's for it's TASF. What is the difference between MFT and BMFT? MFT has this noisy evolution. Does not have a noisy evolution. However, in MFT, I mean, in both the MFT and BMFT, there is an initial fluctuation which has to be accounted for. And in BMFT especially, these initial fluctuations are propagated, and as a result, you have density which gets correlated, and you'll see non-trivial fluctuations. We are interested in this particular work on integrable models. So for integrable models, we know there are like charges are conserved as a result, and they also have to be in involution. You can write an Euler equation or a continuity equation. The expression for current can be expressed in terms of the quasi-particle density in a nice way. And what are these quasi-particles? Basically, if you have a particle which is moving, non-interacting particle which is moving with some velocity, but because of interaction, this scattering shifts, it will acquire interaction, it acquires scattering shift, and there's effectively the quasi-particle moves with a new velocity, which is effective velocity. And this equation basically governs how the density of quasi-particles changes in time. In doing so, we have already assumed that the system is in local equilibrium, but now it's not Gibbs equilibrium, but it's generalized Gibbs equilibrium with really n Lagrange multipliers, which is a bit difficult to handle. But TBA comes into play and says you can hide it under the density, and you're back to doing whatever you want. But okay, this is all good. But then what about experiments? Turns out even in experiments, this has been verified. Between conventional hydrodynamics, when you write only 3 conserved quantities versus a generalized hydrodynamic description, generalized hydrodynamic description gives better, I mean, clearly better results for the gas of Linear gas confined to a harmonic trap. we are going to use these hydrodynamic equations to study ballistic macroscopic fluctuation theory, which has been already done in this article. The main idea is you have an initial density. I mean, let's say you have a system, there is an initial temperature profile. This is a typical temperature profile, but you create a sample an initial state, there will be fluctuations around that. And these fluctuations will have a non-trivial energy with respect to the base value, and that is given by this expression. Now you have to evolve these fluctuations via the Euler equation, and you write the propagator of the charge at a later time. Once you have this, you can compute any observable you like. For example, full counting statistics. All you have to do is compute the Kumlin generating function, do the saddle point, do Euler scaling, do saddle point approximations, and what you find is initial profile is going to be will evolve according to this Euler equation. Even the auxiliary field will evolve. I'll describe in more detail when I talk about our approach. And then this is coming from initial condition, and these two terms are coming from the observable. And once we solve the saddle point equation, you can compute the Kumlin generating function and Kumlins, barring all these regularity conditions, which I'm not going to discuss here. Now our approach is, okay, this is a very nice approach. We have a slightly different approach where we want to work with point particles. We can map integral models to point particles. The best example is hard rods. In hard rods, when you have two hard rods colliding, they will collide and then move away. But if you think of it, the momentum carrying particle, it's going to acquire a jump. And you can describe the trajectory of the quasi-particle from the free particle evolution. Basically, I mean, for two particles, it's very trivial because it's going to evolve in a straight line. Every time there is a collision, you have to give an extra shift. But when you have multiple particles, how do you do that? In an ordered system, Tonks has told us what to do. If you have ith particle, you have to count how many particles are there to left of I and to the right of I. That is going to give us the position of the ith physical particle in terms of the free particle. But when you have no ordering, in a sense, quasi-particle can be in a different ordering. You can describe the quasi-particle. Basically, this computes exactly how many particles are there to the left of I and to the right of I. Now, this is a microscopic description. Corresponding to this, there's a hydrodynamic description for hard rods. When you can map this hard rod, and this effective velocity is the changing because of the extra shifts which are coming due to collisions. You can map this generalized hydrodynamics to a free particle hydrodynamics by basically coarse graining this and then relating the density with the normal mode density, and you have this free particle evolution, because here there is no information of the interaction. Everything is hidden inside the capital X now. This is not true. This is not only true only for something like hard rods. In principle, it is true for generic integrable models, and the way to do that is to work in normal modes. And instead of the scattering shift, which was like the shift effective rod length, which was A, now you have a rod length which depends on the rapidities. For example, for Toda, it will be like -2 log theta minus theta prime. And now you have to work in the new coordinate system. Instead of working with interacting coordinates, you want to work with either non-interacting coordinate or free coordinates. And you relate this is the interacting, you do the gridding of the whole phase space, and you see whatever density, normal mode density you see here is related to a different point in free space and there's a free density, basically this sentence. And once you do that and you write the evolution equation for R, you find that it's again free evolution. There's a subtlety which I'm just ignoring, but it's more of a boundary information. But as a result, these are free evolutions. Now we know how to, we have simplified our equation, which was a bit more complicated to hard rods, and now we can use BMFT. That's the idea. But before that, there's this interesting, this mapping, which is now at the level of hydrodynamics, is actually true even at the level of microscopics. The main idea is, when, let's say, for example, a Toda model, when two Toda particles are interacting or colliding, undergoing scattering shift, they will have a trajectory like this. What this mapping is saying is, okay, whatever is happening here, maybe I don't really care about that. What I care about is this scattering shift, and this mapping is exactly accounting for that. And how do I construct this particular trajectory of interacting particles. I know how the free particles are going to evolve. I substitute it here and try to invert it. For 2 particles, it is easy to invert. However, for n particles, it's a bit more complicated, but you can do it numerically. So the main idea of this mapping is any interacting configuration can be mapped to free configuration. And then from there, you can construct trajectories of the interacting system because you just have to do this mapping. And this mapping is slightly more complicated. And Andrew is going to talk about this mapping in more detail. Interestingly, this mapping is actually very, analytically shown to be true for Toda lattice. And this mapping has already been proposed in these 2 articles. And here we'll show the simulations. Now let's go back to what we wanted to do, BMFT. Now we know we can do a free particle mapping, but again, right now we still don't know how to impart initial fluctuations. And for that, that information is hidden in the free energy. Now we are going to compute the free energy of the free particles, which is like, as Kiran and everyone had mentioned, that it's a simple undergraduate problem. That's what we do here. Basically, you divide the phase space into multiple strips, and within each strip, you have a typical profile, typical expectation. Around the typical, there is a fluctuation. What is the exact cost of that probability or free energy? That is basically within the strip, there is a multinomial distribution. And outside the strip, there is a binomial distribution. If you combine everything into the free energy, into the probability, you will find that the free energy is given by the exponent. This is for free particles, free classical particles. What about quantum particles? Well, you can do the same analysis and you can write the free energy for fermions and bosons also. Okay, now we have all the ingredients in place. Let's do our BMFT analysis. You have initial probability distribution of the initial fluctuation that is being propagated by the free evolution. And then you have a propagator at the later time. Now, whatever observable you like, for example, full counting statistics. Full counting statistics, what it is doing is counting how many particles are crossing from the left to the right in time t. But now these are in interacting coordinates. We want to work with free coordinates, right? So we have to do a variable transformation to go to mapping to point particles. Now all the details, all the nasty things are hidden inside the observable. The 0 in the interacting coordinate is mapped to a new location in the free coordinate, because you have to do this mapping, which will involve density, is slightly more complicated. And as a result, you have this mapping to free particle, which is complicated. Okay, it's okay. It's still, we can continue with our cumulant generating function business. We want to compute the cumulant generating function. We have to enforce this delta function, which is basically the Euler equation or the free evolution. This is the initial probability distribution of the density profile, and this is our observable. You can represent the delta function as Fourier representation and combine everything in terms of an action. And then you do Euler scaling and say, okay, this action is actually proportional to t, so we can do saddle point analysis, and these are the saddle point equations. What does the first saddle point equation say? It says that my free density evolves like a free evolution. Even my auxiliary field corresponding to the delta representation is free, but the boundary conditions are now slightly more complicated. This is the free energy. For classical, it will be rho log rho minus rho bar. And for quantum, depending on fermions and boson, it's going to change. Okay, these are some expressions. But now we can solve for this saddle point equation and compute the cumulant generating function. It's just given by this expression. While the details of this expression are a bit complicated, we have a formal expression for any generic integrable model. From here, we can, in principle, compute all the cumulants up to barring the regularity conditions. But what we have done is to compute rate function for homogeneous case and check with numerics. You do hard rods, you create the sample and do evolution, multiple evolution, compute how much charge has crossed in time t. And basically, you see that the rate function is different from, typical fluctuation is different from Gaussian. This is a verification of what we have done. And also our expression matched the existing results. Okay. And then we also compute the normal mode density correlations, which is basically correlation of the normal modes at 2 points x1, x2 at time t1 and t2. They are given by, because these are normal mode densities, they are directly mapped to a free particle location L1 and L2. And then these are our new observables. We just have to write a generating function, do the whole analysis of Euler scaling, blah, blah, blah. And then we have the saddle point equation. And this saddle point equation has slightly interesting feature. This is still a free evolution, but the auxiliary field have a source term. Again, you can solve it using a characteristic solution. And what you find is the correlation function is just given by this. We have a formal expression for generic integrable models, but here I show it for hard rods. For hard rods, what is this has been done in this article and independently in this article with a similar point of view, but this is done using microscopics. Hard rod, the correlation is slightly interesting. There's a local part and there is a non-local part. Basically, this is the long-range correlation which comes up. Even though initially the correlations were local, because of Euler evolution, there is a non-local correlation. And our expression basically match both the expressions. I'm not so sure about this, but this definitely. And then, okay, so these are the existing things which we have connected to. But what new things can we get from this mapping to point particle? And this work is done with SOMO. And what we have seen here is, what we can compute here is, take a tracer particle and we can study its statistics. But what is a tracer? In this GSD business, quasi-particle tracer is a tracer which moves with a specific velocity, right? But what here we are looking at is from a MFT picture. In a single file, there will be, because of single file nature, the particles cannot cross each other, so they will be trapped inside. As a result, and we want to study that observable. And that can be done by defining the quasi-particle position in terms of the density. Actually, this quasi-particle has been already studied. Going back to physical tracer, what we have to do is, say at any time t, number of particles to the left of me are going to be same. That's what this enforces. But this, as a result, we can relate the position of the tracer particle with the density of quasi-particle. Go back to the original, not original, but the free coordinates. You have the relation between quasi-particle in interacting variables and free variable, free space. Do the whole business of saddle point approximation, generating function, blah, blah, blah. And what we find is, for the homogeneous case, if these were not rods but free particles, you can compute it easily. And you find this is the generating, the rate function. What about rods? A simple expectation would be, okay, rods and point particles are very straightforwardly related. All you have to do is shift all the particles. Turns out, okay, by shifting, you are basically contracting the length. As a result, you're increasing the density. So if you want to understand the rate function of the rods, you compute the rate function of the free particle and then just modify the density to free density. This we verified from microscopic microscopic calculation as well. And this is the expression for a rate function. Something interesting is happening. I guess this universality feature is already known. What we find is rate function is actually exponential for large trajectories, very rare trajectories. Okay, this is one tracer. We actually compute the true tracer also. Expressions for true tracer are a bit more complicated. But again, you compute it for free particles and you can relate it to the rods by doing a mapping. Here, what is happening, we have two different rods. Let's say first rod is at origin, second rod is some L distance apart. Because when you contract it to free particles, the length, you have to adjust how many particles were in there. It is that adjustment. And this is the density because now you're working free. And this L also gets contracted. This is what is accounted. And basically, you can relate rod and free. Okay. I'm a bit fast, I guess. Okay. Free and rod. So, okay, fine. This again, we have verified it microscopically. But what about Okay, motivation is Brownian now. How can we connect this to Brownian particles? One thing which I forgot to mention is here speed is t. For Brownian free particles, this whole tag particle business has been done in this article, and they find the same rate function as us, of course, but the difference is now it is square root t. This speed is square root t, suggesting that the quasi-particle, sorry, not the physical tracer in the ballistic case is moving diffusively, but in the Brownian it is subdiffusive, right? We can extend our computation for even hard rods, Brownian hard rods, and we find that the rate function is only difference is the square root t, and the rate function can be computed from the free in a straightforward way. We compute for two particles also, and we see the same thing, except the scaling, time scaling, the rate function are exactly the same with this. Yeah, this is what we compute, and we verify it from a microscopic, we do a microscopic calculation to do this. So BMFT and microscopics are matching. Finally, what we have done is BMFT description using point particle mapping, and we found that the hard rods have non-Gaussian full counting statistics, and we see generic integral models developing long range correlation even though without with the local correlation. Yeah, and then we find that the ballistic rods are moving in a diffusive way, and diffusive rods are as known as subdiffusive. Thank you.
Thank you very much. Are there any questions? No, doesn't.
Let me try. Yes, okay. Thank you very much for the talk. I enjoyed it a lot. I have a question. Could you imagine of coloring the hard rods? Like now you have just one particle species, but you could also have like two component hard rods that probably is getting closer to the single phi that, for example, Jacopo studied, but in this kind of picture. You should have like colors the same mass, and when they scatter should have some possibility going through or bouncing back. Still preserving integrability. I do not know if it's possible. I'm just wondering.
So from the microscopic point of view, because we write a propagator and then do this evolution business, I'm not very sure how to account for this swapping which you are suggesting. It's a swapping you're saying, right? I'm not exactly sure how this swapping has to, I mean, for our description to work at the point particles, can we map it to free particles? And if in free particles, we can do a two species business and do this stochastic shift, which you're talking. Maybe it's possible, but I don't see it exactly how to account for it.
Two limiting cases where like immediate particles have different colors, and when they scatter, just exchange color. Always, that would be trivial mapping. Or if they don't exchange color, and so they bounce back, that I think that is also kind of a trivial case. I do not know if it is an intermediate regime as well. But that is more a question if it exists interbody discretization of hard rods with two species. So, and I do not know the answer. I just wonder if you were aware of that.
Yeah, I'm curious as well. I would like to discuss more because I don't know.
Okay,
this. Yeah.
Thank you a lot.
Yeah. Giga?
So two questions. I mean, here you sort of this mapping to point particles. How general is this? Because I mean, as we heard in the last talk, right? I mean, there are integrable models where you sort of have radiation, which sort of is not localized. I mean, can you do something similar to that in that
For
case?
radiations, I mean, yeah, I don't have an answer. But for particle systems, yes, it's going to work. I mean, it's at least expected to work. And for TODA, it's been clearly shown to work. So.
And then second question, on the conclusion slide, you had something about typical part of FCS is non-Gaussian. I mean, I missed that. What exactly is that?
Okay, so we have a rate function. Maybe I can show you. Yeah, we have a rate function. And if you take the second cumulant by taking a second derivative of the cumulant generating function, from there you know the variance. Corresponding to the variance, you can write a Gaussian. And you see that the Gaussian and the rate function are very different.
But I mean, this I mean, typically this is what you'd expect, right? I mean, the typical fluctuations are only the curvature of the rate function should match the variance of the Gaussian. I mean,
That is true, but this is still in a typical regime. Even though I've just shown it a rate function, it's not really important sampling. It's like these are still typical fluctuations.
the red curve is what?
Red curve is the theory.
But it's the rate function.
That's true.
No, this is what.
I mean,
So maybe can I make a quick comment about radiation? Supposedly, the conjecture would be that if you just change the distribution, the entropy, make it really genes, and use these particle models, then it would work also for radiation gas. That would be the conjecture. Huh? Yeah, I mean, so.
No. Yes. Also in quantum mode excitations tend to be localized, plane wave for a single particle. Okay, exactly as radiation, but still you can do it because you can imagine wave packets. Of course, it's not point-like a good description, but on a hydro scale it is. And this is just supposed to capture maybe all hydrodynamic order, but still hydrodynamics. So it's not a proof, but I would not be surprised if it works.
Yeah, so for the tracer diffusion, I think the diffusion constant was calculated by.
but this is a physical tracer, right? We did not check that, but I think it does because in this article, I did not check, but I think it should match. Yeah.
Other questions?
I can check that and yeah.
So you computed correlation functions in a local equilibrium, right? And you observed this emergence of long-range correlations. Did you also compute correlation functions for the partitioning protocol?
For partitioning protocol?
Yeah. So in that case, not only this initial local equilibrium, but also the sharp initial condition. Sorry, not the initial local equilibrium. Sorry, the sharp initial condition alone induces some.
Okay, so I think that is for partitioning protocol only. This. Okay, I don't remember now, but we can extend our ideas to partitioning protocol in a straightforward way. But you are asking like what happens there? So will it have some extra piece other than this when you do the?
So the idea is that because of the sharp change, macroscopic is additional information not captured by Hydrodynamics.
Yeah, I mean.
So then it's not. Then probably not. But the question is that these particle models produce the atom.
Maybe we have to check it explicitly, but I don't know directly. Yeah.
I'm not sure because it's like in quenches when you do like the homogeneous quenches, particle pair, they are long-range correlation of that type.
No, but they're polynomial. I mean, this is the same that we found with Mewes.
You do produce long-range correlation of that type. I think, but okay, anyway, you can discuss that. Other questions? Okay, so I think, yeah, thank you very much for the talk, Jitendra.